Okay. I'm going to go back. I'm not going through all the problems that we went through. But I'm going to go back and talk about the topic we are at hand. That is trigonometric intervals. So these are going to be these are the forms of integrals right here. Don't worry about the forms just yet. But that in red, you're going to need to know. Now, when I've told you and I tell you, you need to know, have I ever lied to you? And so this was a student. Idea is to put a slide together of all of the must-know trig identities. These are it. You need to know these, every single one of them. And on the video, I even talked about how you get some of these and everything. But you got to know these are collected into similar types. Okay, the top circle are the basic ones. We've derived these in class right here. One of them we don't actually use very much is cotangent squared x plus 1 is cosecant squared, but that one could go in there too. We don't use that one so much. These are half angle and double angle formulas. You gotta know them. And you gotta know them. And I mentioned last time that these over here, these come from these. Because these are sine and cosine addition formulas. So the sine of 2x is just sine of u plus u. And if you look at the video last time, I showed you how that turns into that. But you got to know these. These are the even or odd formulas. Right? They are must know. You're going to do. You have pain in your future if you don't know that trig. Right? So I went through integrals of this form. If either sine times cosine to different powers, if either one of them is odd, that's the easy case. Because what we did, you notice here in this example, cosine was odd. We peel off one of the cosines, and then you have cosine to a even power, and then sine to an even power. So the cosine to an even power, I substitute 1 minus sine squared squared, that's cosine to the fourth. We square all that out. Since we've peeled off that extra cosine right there, you wind up getting sine to a bunch of different powers here. At this stage of the game, I'm going to erase this, but at this stage of the game, you have sine to a whole bunch of different powers, all times cosine. So if you have sine to a power times cosine, you wind up at the end, this was our goal right here. That cosine, once you multiply this stuff out, those are sines. You multiply that stuff out, they're sines to different powers, all times cosine. So you got sine to the fourth power times cosine, sine to the sixth power times cosine, sine to the eighth power times cosine. So that's sine, that's a function to a power times its derivative. Function to a power times its derivative, right? And so that allows us to integrate those pretty straightforward. I highlighted what I consider to be the key parts, okay? There's some love. Let's do. When here we have sine to the fifth cosine to the 0. What's going on there? You don't have any cosines. So sine to the fifth is really sine to the fifth times cosine to the 0. What happens? Well, here is sine to an odd, cosine to an even. 0 is even, right? What was the trick last time? Peel off one of the odd ones. Something to an odd power, peel that off. So you took the sine to the fourth, sine to the fifth, you peel off a sine. And we're going to save that because that's going to become the derivative, part of it. Sine to the fourth is sine squared squared. And then I start plugging in for sine. Sine is 1 minus cosine. Square it. Becomes that. So here, look, I have a bunch of stuff. The 1 is a constant, of course. These are cosines to different powers, all times the derivative. That's why you peeled off that sine. You peeled it off and saved it. That becomes this. And this right here, you can integrate. right? Because you got sine there times 1, that gives you this. We know how to integrate that. Sine times minus 2 cosine squared gives you that. We know how to integrate that. That's a function to a power, and almost times its derivative. The problem is the derivative of cosine is not sine, it's negative sine. So you got to put a negative there and a negative there. So you got to watch your negatives here, right? So that was the strategy there. Here, we have a messy case. That was the easy case we just did. If one of them is odd, you peel off one of the odd ones, make it even. Off to the side, convert everything else to the other trig function. And so you have that trig function to powers times its derivative that you peeled off. Here, you got both even. There's not one you can peel off. So you got to make extensive use of these guys up here. What you need to know. If you don't know those, your problem ends right here. You can't move at all unless you know those. Right? You can't get out of the parking lot unless you know these. What are we going to do? Those are for sine squared, cosine squared. Now, don't do sine squared is 1 minus cosine squared. That doesn't help you. You've got to use those half angle formulas. So what do I do? Sine to the fourth is sine squared squared. Sine to the fourth is sine squared squared. So I substitute in for sine squared. Sine squared, according to up there, is 1/2 1 minus cosine 2x. Right? Right? Now, does your YouTube guy do that? Huh? I know, I'm old. I'm really old. Right? Cosine squared, 1 plus. Oh, by the way, the difference in those two, notice, is just this sign in the middle. They're identical except for that sign. Did I mention you had to know those? Have I ever lied to you? When I say you need to know them. Never trust the math teacher. Here's one of my sayings. That one you can trust me. You can take that one to the bank. So when you put those in, it gets messy. You got this 1/8 that comes outside. You got to square that. You multiply them together. But guess what? Once you multiply them all together, you have a trinomial times a binomial. Something with 3 terms in it times something with 2 terms in it. That gives you something with 6 terms in it. Remember I told you I showed you a month ago. I even brought up chapter 8 slides in chapter 6. You remember? I said, if you don't know trig, there will be weeping and gnashing of teeth for all who do not know trig. All right? There will be the coming of the Lord. Right? Judgment time. It comes in calculus for those who don't know trig. All right? Now, when you multiply all this out, you get 6 terms. Fortunately, the 2 yellow ones that are circled in yellow, they combine. Those 2 combine to give you this one, right? The 2 green ones combine. They're like terms. The problem one, though, is this guy here. The problem one is this guy. Why is that a problem one? Because it's squared. If it's cubed, that's good. That's okay. If it's to the first power, that's okay. Constant, of course, okay. This one, we have to use that formula up top there again. So it becomes cosine 4x. So we have to apply that formula up there for cosine again because that one's squared. That's the only way to integrate cosine squared. Yeah. Yeah. Right? And look, it's a mess. I'm gonna leave you the video. But I showed you the approach. This guy right here, I went through with the yellow and I highlighted the hot spots, right? The critical big stumbling block spots. This one's a big one right here. Can you get the antiderivative of that last term? Because you're going to have sine squared 2x times cosine here. Do you know how to integrate that? That's sine squared 2x is sine 2x squared. Do you know how to find that antiderivative? You've got to be strong in derivatives to find that antiderivative. Not okay in derivatives. Strong in derivatives. to find that antiderivative. Why? Because this is U substitution twice. There's U du, but even du needs U substitution. Because you got to get here you got to get the derivative of U on the outside, but to get the derivative of U on the outside, you got to get the derivative of 2x on the outside of that. So there's U substitution twice. No chance unless you are strong in derivatives. Right. No chance. Your problem would end right there. Any of these yellow spots are the end of your problem if you don't know a certain thing, right? Okay, so that's some love for today, really. This one, just a factoid. Those have no antiderivatives. Don't do that. Skip. I actually do not have those memorized. So now today we're going to do integral of the form tangent secant. What we just did was integrals of the form sine cosine. This is tangent secant. Oh, you know what? We got some love here. Hang on here. All right. So let me. Once in a while, I really should look at my lecture notes. I really like it. So now, the thinking changes here. What was the strategy before? Well, look for one of them that's odd. And peel that off if you can. If not, you got to use that half angle formula, right? And that's sloppier. All right, so that's why that was the messy case. Okay? These integrals of the form tangent to a power, secant to a power, they have one easy case, two easy cases, not an easy case. This is not, it's not just messy, this is yucky. And we're going to do it. We are going to do this one, right? That one. The thing is, unless you know what you're looking at, that looks the same as that. They all look the same. Actually, the same as that. What in the world's the difference? Unless you've done a lot of problems. I cannot underscore that enough. Without graphite to the paper, you will never, it just won't happen. I'm not trying to exaggerate. I'm stressing a lot of like what's important, but now is where those weaknesses, they start to accumulate. All right. Okay. So what makes this case easy? Now we got to remember something. What are we looking for? We're going to look for a trig function to a power times a derivative. So this is the format that we would like. We would like trig function to some power in whatever it is. Then on the outside, I want derivative.
Of the same function.
Of the trig function. Why? Why do I want that? That's U substitution. That's another way of saying U du. That's what we're saying. You see how this comes up all the time? It's the chain rule in reverse. But if somebody doesn't know the chain rule was one of those core ones. Remember the first quiz, the first week of class was chain rule, multiplication rule, quotient rule, and power rule. No trig functions, but just those rules, right? The next quiz was what? Applying those rules to the transcendental functions, the trig functions, log, exponential, that kind of thing. Right? I hope now you see why I did that. Because if people do great on that, you're set. That's a happy meal. But when you're struggling, there comes a time of reckoning, right? So this is the format we're trying to get in. Even in the last problems we did with sine and cosine, we try to do that. Sine to a power times the derivative, right? It's cosine, right? Cosine to a power times its derivative minus sine. So that's what we're working toward. That's point number one. Point number two. What is the derivative? Just a reminder. Pop quiz. In fact, we're going to do the tune here. d dx tangent x equals d dx secant x equals. Give me those derivatives. You get 5 extra seconds. Derivative of tangent is? Get one? Get? Derivative of secant is? Right. If you don't know those, you cannot even start. You won't even get out of the park. Not the parking lot. You won't get out of the parking space here. You're going to be. It's not going to be like, oh, I need a jump. It's like I need a jump, gas, and air in my tire. Right. It's like going into a baseball game, only being able to catch things thrown underhand. Right. You can't catch anything in a baseball game. Nothing is thrown underhand. Things come your direction very, very fast, right? So we want to get this one into a format like that. Something to a power times its derivative. Now, we have two options. We could do secant to a power times its derivative. What's its derivative? Secant tangent. Or we could do tangent to a power times its derivative. Tangent to a power times its derivative. Now, the tangent, the derivative is secant squared. Here's the key. When secant is to a even power, we're going to do the same trick we did with sine and cosine. Secant to even power. This is going to be this. Integral. We're going to take a secant squared, which is the derivative of tangent, right?
Why you don't leave it the tangent as secant squared, and then it's going to be secant squared squared. It's going to be secant to the fourth.
Yeah, that'd be secant to the fourth, and I could convert this to secants. The problem is, how do you integrate secant to the sixth or secant to the fourth? In order to integrate secant, I need a tangent. Because now I know secant to the first power, but secant to the fourth power, so when secant is to an even power, peel off a secant squared. So you're going to put a secant squared over here. Dx. And what does that give you here? Secant squared x tangent squared x. right? Those are all multiplied, okay? How is that going to help us? What's the derivative of tangent? Secant squared. So when I do that, I'm intending to convert everything to tangent, except that secant squared. That secant squared I'm saving as the derivative of tangent. So now, when secant is to an even power, when I pull a secant squared off it, it's still to an even power, right? Let me say that again. When secant is to an even power, in this case 4, when I pull a secant squared off of that as the derivative, I still have secant to an even power, just power that's 2 less. It's even. How does that help me? Oops. This is integral. Ready? That secant squared remember those must-know trig identities? Remember those? Secant squared equals? Now, let's suppose you're stuck. I did this before. Let's suppose you're stuck. What were you saying?
1 plus cosine or sine?
You're in the right kind of direction, but no.
1 plus tangent.
Yes. Squared. Squared. All right. That's a base on error. Okay. All right. You should have got thrown out at first, but the guy dropped the ball. So secant squared is 1 plus tangent squared. Now, let's suppose you forgot that. What do? I've told you what to do. You start with the base identity. That's the fundamental trigonometric identity. Now you think, what is it I need? I don't know what secant squared equals. Well, how do I get secant squared here? That's 1 over cosine squared, which of course you know, right? Shake your head yes. Right? So I said, okay, I'm going to divide that by cosine squared, and that makes secant squared over there. Right? Well, if I divide one side by cosine squared, I divide the other side by cosine squared. So I divide through by cosine squared. Why did I pick cosine squared? Because 1 over cosine squared is secant squared, and secant squared is what I need to substitute for. That's why I picked cosine. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. Secant squared is tangent squared. So over here, you see what's going to happen? These are going to multiply into all tangents to different powers, all multiplied by secant squared, which is the derivative of tangent. So what do I have? I have tangent to a bunch of powers, all times secant. Trig function to a power times the derivative of the trig function. So this is going to be, multiply this out, integral. Tangent squared x times tangent squared is tangent to the 4th x, all times secant squared.
So
Then 1 times all that. You see what happened? That secant squared that we peeled off at the beginning is now the derivative of tangents to different powers. I now have my integral in this form here. trig function, in this case tangent, to a power times the derivative of the trig function, which is secant squared. Okay. All right. And you do this when the power of secant is even. You'll learn to spot these, believe it or not. If you do the number you need to do, you'll learn to spot. All right. So this right here is, I'm going to write on one side here. This is tangent x to the fourth power times right here the derivative of tangent. Trig function to a power times the derivative. This is the same format. Trig function to a power times the derivative. What does that integrate to? Trig function to the next higher power, tangent fifth, divided by the new power. 5. Plus tangent squared times its derivative, tangent to the next higher power, divided by the new power, plus c. Right? Plus c. So you do that when secant is to an even power. Secant is to an even power, you factor off a secant squared, which still gives you secant to an even power, times a tangent. You convert the secant squareds, because this is to an even power, you convert those to tangents, you get tangents to a bunch of powers times its derivative.
So what'd you do to the secants?
What happened to the secant squareds? They disappear, because when you have suppose you have that. And suppose this is your integral. Well, integral of u du, here. The integral of u to a power du, that equals u to the next higher power divided by that next higher power plus c. Because if you do the chain rule, remember the chain rule. That equals, I should do that, sorry. To the nth power, that's going to be n times n minus 1 power, then the derivative of this comes out. Maybe I should just put du there, right? The derivative of the inside comes out from the chain rule. So when you do u substitution is the chain rule in reverse. U substitution is the chain rule in reverse. So that means the derivative goes back in when you take the nth derivative. Integrating and differentiating are inverse procedures, which is why when somebody doesn't know derivatives, you're not going to do nth derivatives. It will not happen. Sometimes I'll say it's harder to do. I've taught calculus long enough to know you can't. You cannot do nth derivatives unless you know derivatives. And back to my old expression, what's the secret to doing well in calculus? An ice cold mastery of derivatives. Ice cold. That's the key. Case number 2. What if m is odd? The other one, n was even. You didn't care what m was. Here, m is odd. You don't care what n is. Now, if m, what is m? That's tangent. Okay, now watch. Gasa. What? Gasa. If m is odd, this is odd. Instead of taking a secant squared off, we're going to take a secant tangent off. We're going to peel a secant tangent off. So what we're going to do is going to be integral. Over here, we're going to put secant x. We're going to take a secant tangent off. Then what's going to happen? You're now going to have tangent, not to the m power. It's odd, right? It's going to be to the m minus 1 power, which is even. Right? It's even. Times secant x to the n minus 1. Now, you don't care if n minus 1 is even or odd. Now, why is that a good thing? Because what is the derivative of secant? I asked you that right back here. Secant tan. So good, look here. If this is even, and I have secant to whatever power, doesn't matter if it's even or odd, I have here the derivative of secant. This right here is d dx of secant, right? Tangent is to the even power. I can convert that to secants. Because if 1 plus tangent squared is secant squared, tangent squared is secant squared minus 1. Go back to here. This little manipulation here. Tangent squared is secant squared x minus 1. But that's, I got to have tangent to an even power. So guess what? If tangent is to an even power, even means it's, let's suppose it's 2 times k power. That's an even power, right? Then this is going to be integral tangent squared x to the k power times secant n minus 1 x times secant tan. So this becomes, what am I going to do with tangent squared? 1 minus secant squared. That's what I'm going to do. That's going to be 1 minus secant squared to the k power. Right, so this is going to be all right. You know what? You've been writing a long time, haven't you? You started later. You know the test, but slide my mom. Jump out. Oh, it's wrong one. Wrong chapter. 35. Okay. Why do we do all that? Because this gives us secants to various powers. Secant x to various powers times derivative of secant. So I have secants to powers times their derivatives. Trig function to power times its derivative. All right. What do we do here? Just what we said over there. Secant is to an odd power. So this is going to be integral. What did I say to do? Not secant to an odd power. Tangent is to an odd power. Tangent is to an odd power. So I'm going to peel off a secant tangent x. I peel that off, and I reduce these powers by 1. That is now secant to the 4th tangent squared x. All right? All times secant tangent. Right? So this is the derivative of tangent out here. Oh, did I say tangent? Secant, I meant. So I got to convert all these to secants. These got to get converted to secants. How do I do that? I'm converting the tangent. Because I peel that off, I'm guaranteed to have this is even. Because it was odd to begin with. That's why this works only when this is odd. You peel off a tangent, it becomes even. If it becomes even, you can use this, 1 minus secant squared. So this is going to be secant to the 4th right? Tangent squared is 1 minus secant squared x. Now notice, I got secants to a bunch of powers here. This is all secants here. To different powers, all times the derivative of secant. So this is going to be, multiply this out, integral, parentheses, secant to the 4th times 1 times secant tan. So I'm going to have secant to the 4th x times then I'm going to have secant squared times secant tan.
Isn't it negative?
The secant squared is. So secant squared times secant to the 4th, secant to the 6th, times secant tan. Now I want you to see the logic. We now have secants to powers times the derivative, which I kept in red. That's why you peeled off that thing to begin with, is it's the derivative of what you're about to get, all those secants. So this is trig function to a power. Remember that thing? Trig function to a power times the derivative of that trig function. That's u to a power du. What's the integral? This to the next higher power, which is 1/5 secant 5th x. Secant 5th x divided by the new power. Minus secant to the 6th goes to secant to the 7th x divided by 7 plus C. So those are the two cases. If you have tangent to an even power, I'm sorry, secant to an even power, that was the last case. Secant to an even power, secant to an even, you peel off a secant squared. Tangent to an odd power, you pull off a secant tan, right? Secant tan. There's some love for next time, right? By the way, what I'm doing with homework, when somebody hands me a stack of homework, it's like the whole chapter's full of homework. The most recent ones will get full credit. The most recent 2 or 3. All the rest are getting half credit because they're way late, right? The whole idea of this is for make somebody, incent somebody to look at the stuff between 2 class periods so you keep up. So there's one for home. This is the sloppy case. Because it's easy when secants to the even power, which it's not here. It's easy when tangents to the odd power, which it's not here. So we're not going to nearly enough time to do this today. But this particular case here involves integration by parts, usually a couple of times. Integration by parts a couple of times. And you're going to wind up with secants to strange powers. Now, remember, we did the integral of secant. For this here, you're going to need the antiderivative of secant. I told you you either need to know it or know how to get it. And you're going to need the antiderivative of secant cubed. You're either going to need to know it or know how to get it. Both those I derived in class. Take your pick. In my opinion, knowing how to get them helps you remember what they are. Right? We'll leave it there. Have a good weekend. Do some calc. Let me know how I can help. Come hit me up. Office hours or Monday night. Spark. Last Spark. So I think there's going to be, they're trying to have special refreshments or something. As if I would not already be enough of a draw. Okay, really. But, you know, I know. All right, let me close this.
Can you put the video real quick?
Yeah.